Good morning, good afternoon, and good evening, everyone. Thank you for joining us today, and welcome to the DAS RCN webinar on DAS Data Wrangling. I'm Casey Adderhold from the Incorporated Research Institutions for Seismology. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. This webinar will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel. Should you have a comment or question as the webinar unfolds, please clearly and concisely type it into the chat box on the Zoom control panel or use the raise hand option. During the Q&A periods or discussion periods, we will read your question and comments to the presenters or call on you to unmute. If the webinar happens to crash due to Zoom or internet issues, we will reboot it. Just click the webinar link again. Automatic captions are available to be turned on and off on your Zoom control panel. Use of distributed acoustic sensing is rapidly expanding in our community, prompting the initiation of a research coordination network to facilitate workshops, tutorials, and other opportunities for sharing ideas and resources. This is one in a planned series of webinars on different topics within distributed acoustic sensing. I'm going to pass this to DAS RCN Data Management Working Group Lead, Dr. Jerry Carter, now to get us started. Jerry?
Thank you, Casey. So let me hold it. My screen is not being shared yet. Yes, there we go.
Got you now.
There we go. Okay, so thank you, everybody. My name is Jerry Carter, and I am a seismologist and the Director of Data Services at IRIS. I want to welcome all of you to this, this webinar and appreciate your interest in the subject. So what are we talking about here with data wrangling? And what does this data management working group do? So primarily what we're interested in is the metadata content. We want to look at what are the community standards and so forth. And as you probably know, you get some metadata that comes out of a DAS interrogator or interrogator unit, but it's about the interrogator unit, not about the cable or anything else. So we're looking at that kind of content, what should be in that content. We're looking at what data formats are commonly used by the community in when they're dealing with the DAS data. We're looking at general use derivative products. We all know that DAS comes with huge data volumes or can come with huge data volumes, and those are difficult to store and to transport across the internet. So by using a derivative product that might have a smaller, should have a very much smaller volume, then we can then at least get the data out to people in a reduced form so they can look at it and do some work with it before they decide they might want to go back to the full resolution data. And we also are looking at data storage and access, so that we're talking about the discovery, selection, transport, and computation associated with DAS data. And finally, so today in the webinar, what we'd like to do is we have a presentation by Rob Mellors and Kathleen Hodgkin on the DAS metadata considerations. We'll have a little discussion about that and then follow that with a DAS derivative data products by Verónica Tribaldos. And then finally, I appreciate everybody who filled out the survey. And if you haven't filled out the survey, I encourage you to do so. And I'm going to present some preliminary results from those, from that survey and see if we can get some discussion going on it. So with that, I will turn it over to Rob and Kathleen to talk about the metadata.
All right. And let's see. Right. Thank you, Jerry. Yeah, I'm Rob Mellors, and I'm just going to present an overview of some of the metadata discussions we've had during this working group. And they're by no means finalized. It's more concepts and trying to figure out where we want to go, try to come up with a roadmap of how we want to deal with the metadata. And just to give an idea of the scale, I think most of you are probably familiar with DAS data, but this is a shot of the Calipatria earthquake collected by Jonathan Franklin and Imperial Valley Dark Fiber team And so, it's lots of data, but it's good to know, things like response, location, and all that kind of thing. So first, do we really need a metadata? Or can we just use existing ones? And our conclusion was, yes, we do. Existing things like seed that are designed for point sensors really don't work very well. I mean, for example, we don't have any really a pole and zero file for DAS. Active type source experiments where you have lots of nodals are a little bit more similar, but it's still, the measurement is fundamentally different. We think we need to capture that in the metadata. And so we basically tried to take a shot at it, defining that. We based and then did a test case on existing data sets. It's incomplete, but we have to start somewhere. And so right now, I mean, there is a lot of DAS data collected now, and we're not completely sure what metadata is being collected for this. I mean, for example, petroleum industry has collected lots of data from, and here we have a shot from OptiSense of a downhole well. And then also the intrusion detection, for example, a lot of pipelines have fibers and they collect lots of data. We're not completely sure how that's collected in terms of metadata. We suspect it's essentially a data format. It might be SegWi, it might be HDF5 or something else. And then it may be associated with the report. And I know, for example, HDF is self-defining. So in theory, you can put lots of stuff in there. SegWi tends to be challenging and not necessarily the best fit. And often what they'll have is files and they'll be accompanied by a report. And ideally, you'd like to have all the essential information in a defined standard and hopefully even filled out correctly. So we took a shot at thinking what it might look like. And the first thing is, well, you need an overview. What's the experiment, who, why, what, when? And I think some of you will recognize a picture of the Porotomo one on the right. And then you need information about the interrogators. What kind of interrogator is it? That may make a difference on, strain rate versus strain, what model, etc. And then things like acquisition parameters, pulse length, repetition interval, all sorts of parameters like that. And then the fiber itself is going to have, the fiber and the cable will have an impact on it. It might be an engineered fiber. It might be just a standard single mode. It might be a dark fiber inside a conduit. So that will impact the data. And ideally, that would be recorded. And then finally, you would have the channel metadata, which would have things, the channel, where it is, which interrogator it's hooked up to, what direction is the pulse going. So there's all sorts of data. And a lot of this would not be, as we see, would not be in a normal metadata thing. So kind of test this idea, we just figured we'd try to shoehorn in an existing data set, just as kind of a test. And we picked the Forge data set. This is a Forge is an enhanced geothermal pilot study in Utah, and it's Frontier Observatory and something involving geothermal. I don't remember the rest of the acronym, but what they did a hydraulic simulation basically of a granite in Utah, and it had an observation well equipped with fiber and an interrogator on the surface. And there was one cable, 5 fibers, one interrogator, a vertical borehole. The fibers, I think, were looped back at the bottom. But the key thing was we had a pretty good metadata source. We had the Forge installation report, which really covered a lot of the information that we needed, that we could imagine putting into the metadata. And so on the right, you see kind of a schematic of what the layout was, the various fibers, and then even a schematic of the type of cable and fiber that was involved, which is, if you're trying to interpret the data, is kind of key. So for overview and acquisition, we're imagining something like this. We give a location, the Forge site, Milford, it's a permanent deployment, the investigator, when the experiment was, and then we give a little bit of information about the interrogator. So it's one interrogator, it was a Selexa Carina one, and the measure was in strain rate. And for some of these, we would imagine you would give a fixed number of options. Obviously, there may be others. For example, you might have a DSS versus other strain, but that's kind of what we're imagining. Let's see. And it's, okay, there it is. Okay. For the acquisition metadata, I think there's more parameters than we have here, but basic things like the pulse repetition interval, the sample rate, the gauge length, and obviously some of this on the unit units, the gauge lengths may be changed afterwards, so that makes it a little bit challenging. Channel spacing and measure length of a specific data set, and then timing, a standard one, and then you might put in some information about how whether it was in a shed, whether there was an isolation table, whether there were other effects like that on there. So all of these things will have to be expanded out and codified, but this is kind of what our start would be. And maybe we're really trying to figure out what's the essential information. And then cable metadata, again, lots of possibilities here. In this case, it was a borehole, and you can imagine all sorts of things that outside the casing, inside the casing, grouted, et cetera, et cetera. The characteristics of the cable could be tightly buffered, loosely buffered, or it might even be a mix. I think some cables have both, armored, gel versus fill, and then the dip of the cable, and then the coordinates. That could go in the channel part, but basically this, you could imagine you might have two sets of coordinates. You might have where the cable was actually deployed and another one associated with the channels, and then the installation. Actually, I'm trying to remember why we were thinking installation environment was different from installation, but we had a reason. And then the number of fibers. And then finally, you'd get down to the actual fiber. And in this case, you have, I think, 5 fibers inside a cable. And so you'd have to start and end of it, what type of fiber it is, coding, what maybe the sensitivity, although the sensitivity, that might actually go in the acquisition. I'm not completely sure about that. So there's some uncertainty there. Although engineered fiber will have different sensitivity, and the geometry, of course. If you have a helical, you'd want to give the angle of winding of a helical. And then the channel metadata. So each channel, and this would be, you'd have a location associated with that. And you might have, 2 locations. One is the distance along the cable itself, and then an actual geographic location that was maybe verified by a tap test, for example. And direction of the pulse, it might be going, if you looped it back, it might be going reverse, for example, and the orientation, and what interrogator was tied onto it. And then we had other questions, processing data. So processing and calibration, how is this captured? Do we want to keep it in this metadata? For example, if the data is reprocessed and the gauge length is changed, presumably we would change all that kind of thing. Or you might do other things like stack every few channels to get an optimal signal to noise or downsampling or windowed events. So that's kind of a separate question. So I'm kind of curious what the industry does for this kind of thing. And so basically, I guess I ran pretty quickly there. We believe the new metadata model is needed. It's not completely clear that there's one existing, although there probably are ones existing that we could use adapt. And we've taken some steps towards defining a possible model. And that's pretty much it. Open questions, comments, etc. Thank you.
So maybe people could, if you have some questions, either unmute yourself and ask, or put them in the chat and we can go through them. I know that we have quite a few people here, so maybe putting your questions in the chat would be great.
Looks like Andreas, did you unmute? Do you have a question?
Yes.
Great.
Hi, thanks, Rob. That looks quite comprehensive. My question is, do you also anticipate any user data fields or kind of empty space that people can put in their own comments or data that is specific to their own experiment?
I guess we hadn't included, that's probably a good idea. I guess I'm trying to think, I mean, for example, SegY kind of has that equivalent as the EPSIDIC. I'm not sure if the seed have anything like that. So, but given the number of parameters here, we might, yeah, I think that would be something useful to consider.
I mean, just the general empty fields in SAC, everybody always used some of the headers that were mostly not used, but I think it's good to have every now and then for every field at least a comment section which people then can use, or expandable as it is in HDF5. So people can just put in anything they want, but having some predefined user data 1, 2, 3 is probably, well, I would probably most certainly use that along the way.
Yeah, I defer to others on that. I mean, I guess I would like to avoid the SegY version where everybody has their own special version of SegY. But on the other hand, if you have it definable like HDF, where it's expanded in a kind of predefined fashion, yes, I agree, that would be useful. And it would avoid trying to think of all possible cases beforehand, which you can never do. So yeah, thank you.
Jigen, do you want to go ahead and
Yeah, sure. So I think I just don't know whether in this community that we can reach agreement on what the data format we plan to have, or majority data format we plan to have. The industry almost have agreed on HDF5. However, HDF5, the problem with HDF5 is such a flexible format. It's basically just a file folder with a whole bunch of attributes in each file or each folder. So I wonder if IRIS or this community can come up with a standardized HDF5 format where you basically just write one Python interface or C interface, so you can read any data that at least from this source. I think that will be great and very, very helpful. And also back to the user data, user metadata question. HDF5. You can standardize those fields that actually contain certain number, but you have the freedom to add as many fields as you want in that file that can meet user need. So I think it could be a good solution if we approach that.
Thanks, Jigen. I think those are important comments, and I appreciate the fact that we would like as a community to get everybody's input on the format that might be used. And I appreciate the suggestion that maybe IRIS could lead that effort. So we'll definitely be looking at that.
I think
Herb?
there's a question in here that I think Herb can answer from Matt Fouch. I'm just going to read out loud real quick. Rob, thank you for the excellent overview. Are there other similar DAS RCNs worldwide with which to collaborate as these metadata and other standards are being defined? And I actually want to kind of pose that to Herb. I believe our RCN is a worldwide phenomenon, and everyone is welcome to be participating, but we could probably continue to reach out to folks worldwide.
We are certainly open to anybody who wants to join. But in fact, as I was listening to Rob's excellent presentation, I was curious about formal groups who set data standards. IRIS being involved is certainly very good because of its mandate to archive seismological data. But are there formal bodies? I mean, SegY is SEG. I wonder if somebody could comment on whether or not there ought to be some overture or connection to groups that set standards.
So could I answer this in two parts? First, we did have substantial impact from, I think, Helly Peters, if I remember correctly, Helly Peterson and some others. And the data model we developed was really based on input from some of the Europeans on the committee. If I remember correctly, this was back in, and so Kathleen and I basically just adapted what they suggested. So we definitely did have significant interaction with the European community. For standards, perhaps others have other ideas, but I know CFOM, I don't know how to pronounce it, they have a number of documents, maybe on standards for testing DAS. Anyway, I don't know if there's any standards for data formats. Perhaps others can illuminate that better.
I can jump in because I have attended some of the CFORM meetings, and there was a pretty significant effort across the industry, almost like 4 or 5 years ago, to sort of standardized DAS format. They have a pretty good standard on the DTS format, and now they standardize the DAS format. That's where the PerMel 2.0 coming from. And so that's become the industry standard. But the problem, PerMel 2.0 is also a very flexible, format. So each company has its kind of own PerMel 2.0. So I think, we can definitely build up on top of those, and but we need to be a bit more rigid on, as simple as what the file name or metadata name should be in the HDF format, then will be great helpful. The goal is actually just writing one version of code and give you access to all type of data, right? So. I will try to find the document and post it on the chat.
Yeah, thank you.
Hi, everyone. Just to add to the comments made, CFOM is very active, and the MS-P02 has been under revision, but obviously focuses on mainly testing the instruments. But there's Energistics that is also working around the data formats with oil companies. And also more recently, there's IEC standards, which trying to build some standardization protocols for DAS measurement and data format, which is a European. And also we've been engaged in IEEE more recently, that they started a committee to look into the standardizations of DAS. So, and obviously, IRIS is very active as well. So it's good to get a unified specifications among everyone. So.
Thank you. And I'll just add that Ray Williman in the chat had mentioned that FDSN endorsed SEED, not IRIS alone. So just adding that for the recording. Ross Henderson, did you have a comment on this thread or a different question? Or no comment at all? That's fine.
Sorry.
No worries.
Sorry. No, I was trying to fill out the survey.
Oh, okay. Sorry. No worries.
Sorry.
Go ahead and or mute yourself there.
Okay.
All right, there's another comment here. I'll just read aloud. Patrick Pites says to everyone, there is also the adaptable seismic data format ASDF out there. It might not be ideal to store DAS data since each channel is its own data set with own metadata, which can be a bottleneck in input and output. Many of the ideas behind ASDF could be of interest for next gen DAS format. Not sure if the working group discussed this in the past, but it could definitely be interesting. So thanks for that.
So I'm curious about the next steps. Mahmoud, what would you propose our steps to be if we wanted to reach out to some of these other organizations or?
I think this thing is evolving. I mean, the most established group that I could think of in terms of DAS and some of the working group that I've been involved is CFOM. And I think the IEC is building on that, and we tried to issue a document which tried to capture, and compare the two documents. And then IEEE is just something that we started the discussions about a few weeks ago. And we're trying to really first make sure that there's a common understanding or definitions of the system parameters. And obviously, we have modified some of the picture that you just showed in terms of better understanding of that 2D document that you show the definition for spatial resolution of gauge length. And I think those things that then could find a good way of how we then could load the data. I think, adding some additional fields for metadata or that is possible. So, I mean, I don't have a very good answer, but I think maybe we could think that The way IEEE was reach out to CFOM was selecting some member that we are working on MSP-02 document together. So we are now interfacing with them, making sure there is a good communications between the working group in different sectors. You know, all serve different purposes, but I think a selection of people here that could be maybe get together with the CFOM members and myself involved, and there is 2 other colleagues that also involved in as a leading the group at the moment. And I think that could be a good way of at least starting communications between different groups. And we also have IEEE group as well. So, you know, so it could be a selected members, whoever wants to be volunteered, and then we can set up a meeting, at least say, you know, where we are with our thoughts on documents. And the other thing is a lot of the work, I know we're talking about data in a general way, but it's good to bear in mind the applications, because, you know, some of the applications would also drive how the data needs to be set or formatted. So there's work to be done, that's for sure.
Thank you. Yeah, thank you very much.
It's good to see so many familiar faces. Actually, I'm glad I did. I have been isolated for quite a while.
Yeah.
Yeah. How is everyone? Good. I'm, by the way, negative in terms of COVID.
Herb, your hand is still up. Did you have another comment or question?
No, sorry, I'll lower it.
Okay.
And I'll just read quickly here. Eileen Martin agreed with Mahmoud's comment about applications, at least differentiation of active, triggered, and passive continuous applications. So very good point there. We did have one question going back a little bit from Dennis Reedy. I think there was a mention of storing both raw and process data with the non-commitment increase in storage. Could that lead to a decision to store one or the other, neither of which I would think would be good? I don't know if there's any comments on that. Maybe that's a bigger question for later. We can address it.
It is a big question because there's a huge commitment, of course, for storing all of the raw data, and of course we're looking into both that, and that's part of what is in the survey. There's some questions about that, so we'll get into that a little bit later. We're trying to find out what the community actually wants, and what we might do for the community in the future. So we'll maybe you can contribute again to the conversation when we get to the survey. So perhaps we should move on, and if there's no more comments, maybe we should move on to the next presentation by Verónica Tribaldos, who's going to talk about, she has worked on some proposed products, reduced size products. And so, Verónica?
Yeah, so hi. Yeah, actually the question was a good lead into the talk, because we're going to discuss basically that. So let me see if I can share my screen here. Okay. Does all look good?
Yep, looks great.
Okay, great. Yeah, so hi everyone. My name is Verónica Rodríguez Tribaldos. I'm a geophysicist at Lawrence Berkeley National Lab, and I will be talking about a different aspect of dealing with DAS data, which is basically how to handle these really large volumes of data that we generate in DAS experiments. And one suggestion that we want to discuss with you all today is generating these data products that are specific for different applications, so that we can basically share or work with that, or even store only those products instead of storing the full raw data set. So by now, I'm sure everyone in the call know what DAS is. But so the main idea is the distributed acoustic sensing is this new technology that basically converts a fiber optic cable into a massive array of broadband seismic sensors. So current systems allow you to record continuously data along fiber optic cables that can be as long as 30, 40, 50 kilometers with spatial density of 1 meter or even less. So that means that we are generating, or we are basically converting this fiber optic cable into tens of thousands of individual sensors. And we can do that at frequencies, so we can collect the data at frequencies that range from the millihertz to the kilohertz. Since DAS is, by now we know that it's a very broadband sensor that has a response from close to DC, so basically static strain, where we're talking more of a geodetic tool, to kilohertz, where we are using these high frequencies of the seismic field for near surface imaging. So DAS has been around for a long time. Well, a long time, like basically we can say probably it started being used in the 90s, mostly for oil and gas applications. And in the last maybe 6 to 10 years, it's been used for more, let's say, kind of academic investigations. So currently we can all agree that DAS is one of the drivers of the big data dimension in seismology, due to this really large number of sensors that we can generate with this one fiber cable. So it is not strange currently that one group only generates a petabyte of data per year. So in my group, we've collected over 2 petabytes of data over the last 5 years or so. And this comes with the challenges of how you store this data. How do you manage it? How do you share it? How do you make it publicly available when you want to publish something? So these are some of the challenges that we want to discuss how to face here. So here we have examples of a few, let me get my laser pointer. So we have here examples of a few DAS experiments from the last 8 years or so. If we focus, for example, on the bottom line here, we are showing the duration of these experiments and the associated data sizes. And these range from 5 days to 7 or 8 months, but even the ones that are really, let's say, short, just 4 days, we are generating 4 terabytes of data already. So this is a real issue, and this data size, this is only going to become bigger as we use DAS more and more. A different way of looking at it is just this compilation that Eileen Martin and Nate Lindsay did last year, where they selected a few experiments from the last 8-9 years, and they are showing the summary of the data rates of all of these different experiments. And here on the right, maybe the most striking image is the cumulative data. So all of these selected experiments are generating several terabytes of data per experiment. And by 2020, we had over 800 terabytes of data of these selected experiments alone. And I know that there have been more experiments in the last year, so we are way above these numbers. So this is an example of one of these data sets. So this is just the project that I worked on, so that's why I picked this one. So this is the dark fiber experiment that we conducted in the Sacramento basin a couple of years ago, where we were recording continuously for about 8 months. And we were recording along an array that was 22 kilometers long at 2 meter spatial sampling and at 500 hertz of frequency. So this generated about 250 terabytes of data in total, and about 8 terabytes of data per week. So in this case, it wasn't too bad because we are in Berkeley and Sacramento is just about 2 hours drive. So someone from the team had to go every week to exchange those hard drives. But if you are actually in a remote location, there's probably not a possibility to do that. So we need a better way of doing this. So when analyzing this data set, we realized we could use this DAS data for many different applications. For example, near surface ambient noise imaging using seismic interferometry, generating these cross correlations, empirical Green's function. We can also use it for regional and teleseismic earthquake detection. So we all start with the same raw data, but then we quickly generate these different products that is what's going to be used forward. And we basically forget about this raw data. We don't need it anymore. So this is basically some of the options that we would have. So currently we have this DAS interrogator unit, and in the example of this FOSA experiment, we were generating these 8 terabytes per week. So the first option is store everything in full resolution and we save it in hard drives, and we fill our offices with hard drives. And then we also have these storage servers where we copy the data into to have a backup, and then we continuously need to buy more storage because we run out of space for all of this data, which is okay maybe for 1 or 2 experiments, but of course it's not sustainable for the future. A second option would be exploring algorithms for large-scale compression, and this is something that some groups are investigating, but it has yet to be proven out that it's successful. And the third option is start being selective with the data that we store, and just generate these data products that are specific for different applications, and then don't store the raw data. So this is something that we will be discussing today. So the different communities, we know they're using DAS for different purposes, for different applications. So we're interested in hearing from you what kind of products you would like to see. And it is important to realize that the sum of all of these products is actually much smaller than the raw data itself. So that's why we are thinking about this. So this is a model that we have been thinking about with a few data products, but again, as I was saying, we would like to hear from you. So again, we have in the field our DAS interrogator unit generating these 8 terabytes per week. And now instead of the options that I mentioned earlier, what we're going to do is deploy a real-time edge post-processing system that will be next to our DAS interrogator, and it's going to be processing the data to generate these different products. So we came up here with 4 of these possible products based on our experience. So for example, one product would be a regional teleseismic earthquake data product, where we don't care that much at the really high frequencies, so we can downsample the data to 100 hertz, do a spatial stack to, for example, 20 meters. So we are reducing our weekly data rates to 0.16 terabytes in the case, again, using the example of the FOSA project. A second product would be the geodetic product. So as I was mentioning, we know now that the low frequency components of DAS data can be used as basically the formation data. And for that, we only care about really long-term processes or slow processes. So we can easily go down to downsampling the data to like 1 second, 10 seconds. And even if we keep the spatial sampling to the original sampling, we are generating really tiny products that are very easy to manage. A third one that would also be very tiny and easy to manage would be a noise QC product. If we're interested in understanding the characteristics of the ambient noise that we are recording, for example, we could be generating power spectral density plots with a variety of windows, and that would be generating these data products that are quite small again. And finally, for near surface ambient noise products, we could, for example, have in this edge processing system a code that is doing our cross correlations already. So in a way that we are only saving the empirical Green's functions. And we basically forget about the original ambient seismic noise, the continuous recording, and we only care about the empirical Green's functions. And then, as I was mentioning, there could be many other products that we could be thinking about. So with this model, we would be going from these 8 terabytes per week, 0.4 petabytes per year, to of the full raw data to about 0.175 terabytes per week and 10 terabytes per year for the product side, which is reduced greatly. So of course, the benefits of using this strategy are solving our problem of storage. We wouldn't have to drown in hard drives in our offices anymore. It would make telemetry much easier. We could send data directly from the field to the lab, to our office, and to do QC data and work with the data. It provides a route for IRIS and UNAFCO to archive this data and being able to distribute it in the same way that we can now download data from all of seismometers. We could do the same for DAS experiments. And then it would make science simpler. We would need to spend less time thinking about how to write our code so that it can ingest this gigantic amount of data and think more about what we actually want to do, the interesting things we want to do with it. And finally, it's also a good way of democratizing data. So not everyone has the opportunity to have petabytes of storage servers in their institutions or high performance computing. So this would make it easy for people who want to use DAS but currently cannot afford these things to actually be able to work with DAS data. So what's next is some of the things we want to discuss here today. So it would be great to hear from you, to know what the different communities would like to see as DAS products. So it would be, in the future, we would like to agree on the products that we would like to generate and what are the associated processing knobs that we need to do. Then hopefully in the future, we can come up with a common edge software that we can deploy on the systems in the field so that we can generate these products in a standard way. And of course, working with IRIS and UNAFCO on adding the DAS products to the archives. But there are still outstanding questions. I know as a seismologist myself, I don't like throwing away any data. So I keep saying, oh, we can forget about the raw data and save the products only. That's probably not the solution. We want to have a backup of this data, but what do we do with this? Where do we store it? And do we delete all the data after the on-site conversion? I think probably that's something that we don't want to do. But then where do we keep the field drive? And of course, if we would delete this data, the challenge is imagining what the future processing would be. Like 10 years ago or 20 years ago, we would have thought that noise was not useful and we only care about earthquakes. And now we've realized that the continuous ambient noise from cars are very useful to do other types of imaging. So this is something that we will need to think about in advance, and that's one of the very challenging things that we need to face. So I think I'm going to stop here, and I'll be happy to answer any questions, and we can start with the discussion. Thanks.
Thank you, Veronica. That's a lot to think about, and oh, yes, I agree. Lots of claps there. So if anybody wants to has any questions, Matt, I see has already started off. So.
Hi, thanks for the very interesting talk. I'm watching these slides and thinking about, the 1990s when you had massive hard drives and you're excited that you had 500 meg on a drive and you still had to go back and get it frequently. You're also controlling your sample rates just based on data volume. So we have the same problem again, that's a good problem to have. One thing that struck me about having all those hard drives, and I'm sure IRIS has already been thinking about this and probably the national labs, but there's plenty of unlimited cloud computing out there. So for example, Google, if you have a massive set of data you want to load, you don't push it over the internet. They send you a box of hard drives and you drop it on there and mail it back to them. And then they handle it on their end. They plug it into their fire hose. So I just wonder if that, among other solutions, might be a way to be able to archive the data in some static format and let it marinate while people figure out new and creative ways to utilize the data that they haven't already.
So that's.
I think anyone can take. Jared, you want to take this one?
No, you go ahead, Veronica.
No, I was just going to mention that, I think that the cloud storage would be a solution. I think my understanding, and people can correct me here, is that some of the issues is how long do you store that? Generally, these services, you need to pay for them as well. So how long do you want to keep that up there? All of this raw data, you keep it for a year, you keep it for 5 years, and what do you do afterwards if people want to come back to it in 3 years or something? So I think it's something that it's definitely being considered, but it has its own challenges as well, I think.
And certainly IRIS is looking at storage in the cloud and so forth, and there are many issues to do with it. And Matt, I know that you have some contacts with cloud providers and so forth. So we are definitely actively pursuing solutions like that, but we have to see how it all falls out. So sticking it in, usually there's no cost to putting it in the cloud, but there can be tremendous costs for bringing it out of the cloud. Jijin.
Sure, thanks. I think my question or comments is that will we ever get to a stage that we will be very comfortably deleting the raw data and only saving the data product, right? So I mean, DAS is a fairly new technology. You know, if you think about 5 years ago, that the company still only delivered intensity data. And if we didn't ask for raw phase data, there will be no way that we can even find the low frequency string signal out of there, because that's not the standard deliverable. So, you know, my suggestion or recommendation on that is that I like all your idea, I like all this data product. I think that's exactly what I'm thinking, that we should save and we should publicly available, but we should also come to or seeking for cheap, just like very cheap archive solutions that, you know, we can archive those raw data and make the data product available to the public. And if some scientists find out, yeah, if we you know, look at raw data this way, we can get more information. At that point, then we can actually go back to spend money and retrieve those, you know, raw data and do maybe one more new data product, right? So I think maybe for each product, we can release all this data product that we can come up with, maybe release a very small portion of the raw phase data for the future research purposes. And then just find a way like Amazon Glacier product, something like that, to archive those, and the user can spend some money to extract if they want to.
So we have a couple comments in the chat. I'll just read out loud. Matt Fouch just says, I agreed wholeheartedly with you, Jen. From Douglas Miller, astronomy data sets must have similar or higher data rates to DAS and similar need for precise metadata. So that's a good comment. And then there was a question earlier about from Rob Casey, great proposal, Veronica. Question: with the accelerating increase in both affordable storage capacity and network bandwidth we can look forward to in the next 10 years, would it make sense to place raw data hard drives in vaults, and then a group finds a way to store this raw data in the cloud affordably in the next 5 to 10 years? And I think that's, yeah, what we've been discussing here. So, and I think David Hill, you had your hand raised.
Yep. Yes, thank you for that. Yeah, we've been doing this for almost 2 decades now, gathering tons of DAS data, and it's always the same challenge keeps coming up. One of the key things we found is retrieval. How do you retrieve this, go through the raw data? So we find that by storing the frequency band extracted data, kind of imagery of the data, which is in a JPEG format or PNG, it allows you to go through the data sets very, very quickly and identify what you want to analyze in depth, and then you can recover the raw data from that. So it's always useful to store that FBE data, pre-processed data alongside the raw data we found. The other thing is a lot of the data collection that happens there, you don't actually need the full spatial and temporal recording. What you're looking for is snippets of the data. So you talked about pre-processing earlier in terms of processing the data from its decimating it down in frequency, band extracting the data in some way. But you also might want to do some pre-processing at the edge to actually select the snippets of data you actually want to collect. So whether it be a thresholder or some other form of analysis you've done on the data, say there's an interesting feature of that data. I'm going to put a box around that, and I'm going to just save that one little bit to disk, and I can forget about the rest, but I know that that's meaningful to me. And that can save a vast amount of disk storage if you do that. Now, of course, you've got to get to that point where you trust your algorithms and you trust you're selecting the data correctly. But it doesn't have to be too sophisticated. Quite often, it can be quite a high level selector. So yeah, it's just my 2 pence worth.
And there was a similar comment there from Rick Benson in the chat. The idea that raw data needs to be stored perpetually is similar to the historical seismic data record. Data used to be time sliced for events of interest, then it was decided within the FDSN that continuous data would be stored, and look how that turned out. And then there was a question here from Eileen Martin. Veronica, are there any open source or standardized tools that you recommend for calculating data products in the field during acquisition? My team has been doing this in preparation for a remote experiment, but it's required writing code that specifically integrates with the buffer structures running on the interrogator, so not super portable across hardware.
Yes, unfortunately, Eileen, I don't have an answer for that because I'm just running into the same issues, right? I write my code in MATLAB or in Python to do my processing. Yeah, this takes a long time. So that's something that it would be difficult to deploy in the field. Now, we at LVL, we are working with a team at the Computer Research Division who are developing a code to do some of the things. So we have a couple of pipelines, and one pipeline, for example, is to do ambient noise interferometry. So that code is being designed for DAS data only, and it can be parallelized. And I am amazed that I can calculate months of cross correlations in 3 days rather than a month, which I used to do with MATLAB. So that is something that we are working towards. And I know there are other groups that might be working on similar codes. And it's something that we are looking into maybe deploying in the field soon to test it out. So when we do have the chance to test it out, I'll definitely report back. But yeah, I think these strategies using kind of parallelized it's something that it's what it's used. Now, of course, if you're going to deploy this in the field, you cannot have a supercomputer with hundreds of nodes that you can use, but it's kind of finding the idea is finding this sweet spot. Now we are using it in the post-processing in the lab, and we are trying to adapt it to this kind of edge situation. So I'll get back to you in a few months, hopefully, Eileen, on that.
Thanks. And we've got another comment here from Matt Fouch regarding costs. Certainly companies will have to charge to recover the data, but compared to the cost of collecting these data and the human time to manage it, the percentage costs certainly aren't that high. But I understand the challenges in retaining funds for any operations and management portion of a project relative to the upfront construction and collection costs. And then there's another comment here from Rob Casey, +1 to Ji Jin. What would be important for this group to determine is what the preferred model of working with the data will be. Will scientists want to download raw data sets for reprocessing, or will they want processing close to data with server-side workflows? This can affect design decisions and cost expectations, especially for cloud. And I'll note that that is definitely covered in the survey with that proximity of where workflows are happening for data. And then I guess kind of a question comment, what if important from Douglas Miller, what if important journals required authors to publicly archive sufficient raw data to enable their figures to be reproduced from scratch? The paper becomes a form of metadata. So a few thoughts there. Any comments from folks?
Yeah, that is definitely one of the challenges now. Some of the journals require that you upload your data, and most of the times we have to say, well, here is the cross correlations, for example, that I used to generate these figures and do the analysis. And if you want the raw data, you need to contact me because it's impossible for me to upload this into any. So that's, yeah. And yeah, I think, again, a comment on what Jin was saying earlier is that, yeah, I agree that DAS is very new. So we still don't know exactly all the potential of the technology and all what we can discover. So we all want to keep everything so that, because maybe in 2 years, I look at the data again and I find this one thing, and people want to develop new tools, and that is, it is now, I think, challenging. People would not want to delete all the raw data just now. So that's, I agree, that's something that we might get to this point of being comfortable in the future, but I think it's something that needs to be discussed as a community. And that's why these workshops and the survey are useful, because we definitely need to determine what we might want to do with the data in the next few years.
Ji Jin, you had a comment?
Yeah, I just want to add a comment to that. But it's also depends, I guess it's also depends on the project. If we're actually doing a long-term teleseismic earthquake hazard assessment project, and this whole funding, whole BI of this project is actually focusing on the earthquake, then there's no reason to save like 1,000 hertz sampling rate data, right? You downsample it to 100 hertz, and that's almost secure, your purposes. But if you want to do a smart city project, then you need a higher band. So I guess there has to be some common sense that for the PIs to decide that what type of because keep in mind that even we so-called raw face data, they're not raw data. Raw data is actually coming from the digitizer that the light interference data. Even from that to face data, there's tons of data processing in the hardware that already doing something. So there's no perfect solution. So we have to choose a mid-ground.
Yeah, I agree.
Do you want to move to the survey results then, Jerry?
Yes, I think so. This was a very interesting topic. We covered edge computing and the types of products that we might want, and touched a lot upon whether we can or want to record and keep the raw data, or I don't know if we want to call it raw data anymore because of Jijin's comment, but we'll see. So let me get my survey up here. Oops. Now I'm not seeing it, of course. I know what happened.
You saw the slides there for a second, but it looked like it was.
Yeah, but that was the wrong slides. Here we go.
Okay. Yep, we're good there. And then
Oh,
presenter
no,
mode.
the wrong one also, yes?
The survey results?
Yeah, you seeing the survey? Oh, there we go.
Yeah. And then I think if you just go into presenter mode.
Yep.
Yeah.
There
Great.
we go.
Looks good.
Okay, so at the time that I synthesized the information from the survey, there were 28 respondents, and I know that it had gotten to 30 by this morning, and perhaps even more. So we'll go through them and talk about them and see what we came up with. I just realized that this is very preliminary, and I encourage everybody on this call to go ahead and fill out the survey so that we have a bigger sample rate, or a bigger sample to draw from. So who were the people that were involved in this or wanted to do it? Most of them were using the applications of seismology, but we certainly there were people from, using it for oceanography, engineering and infrastructure monitoring, rock mechanics. Oops, I had 2 oceanographies. I guess it was important. Tectonophysics, hydrology, data science, machine learning, all kinds of, so a wide variety of uses for the DAS data. It's not all just seismology. And I'm trying to move. Oh. Sorry about that. I can't see my own slides because I've got maybe if I do
The
that.
controls, yeah, we can't see those boxes, so we see the slides fine, but
Yeah,
sure
I can't see them because the group that hides all of my. Okay, let me back up here. Okay, so then one of the questions we asked is, well, would you be involved in data collection? And no surprise here, almost everybody that responded plans to both collect and use the data. And a few want to use the data, but not collect it themselves. So they're just interested in general. Should the full resolution DAS data be retained? So this is sort of what we were talking about in the last talk. And about 30%, 28% said, yes, we should keep it. Just to make sure that it's available to anybody, and 71% said, well, it depends. It depends on the application that it was used for. Maybe we only want to keep the downsampled data and so forth. So, and if we go on and look at some of the reasons, then we can publish these later on, but talking about not knowing why we might need this high resolution. The idea is, well, let's try and find a way to keep all of this data and so that it is available for further processing in the future. How we do that, not known right now, but at least it was important enough to so many of you that we try and keep it. But many more people were saying that it depended. And I think that the message that I took from this is that, well, it's it does depend. They would love to have the full resolution if they could, if it were possible, but it's maybe more important to make sure that we keep the data for the purpose that it was collected. And so if you need to, if you're looking for earthquakes or something, make sure that you at least keep it at that resolution, doing the stacking and downsampling and so forth, so that you can have a smaller data set that is easily transportable, but that you keep the purpose of the data sets going. So now, where would it be best to store this data? About half of the respondents said that it should be stored in a centralized repository where the data are available to everybody. Of course, if you were working on an experiment and you wanted to have exclusive access to the data for a while, in other words, put it in some sort of a exclusive use category for a while and then eventually make it available to everybody. But a quarter of the people weren't sure where to put it, and some thought that, another 7% thought that they're best stored by the collectors of the data because they know more about it. So a variety of responses, but I think the overwhelming majority here, not the overwhelming majority, but at least half of the people think that a centralized repository would be great as long as we can standardize the metadata and so forth that go with it. The formats, we talked a little bit about this in some of our discussions early. 15 of the respondents liked HDF5. You'll see that there's more responses here than there are people who participated in the survey, but some people said, oh, I like HDF5 or SegY, either one. So SegY and HDF5 were the clear winners. A couple of people who really didn't care. ProDML, which is an HDF5 based format, was also in there. So sort of interesting. I think it follows the conversation that we had earlier. Then when you're accessing this DAS data, let's assume that there's some sort of central repository. Where would you prefer, if you have to downsample or filter or stack anything, where do you want that pre-processing to happen? And most of the people, 57%, said close to the data repository. In other words, they didn't want to transport all of the data across the internet. 32% weren't sure, and those were the clear winners on the survey. And where would you then want to process that data for your research? In other words, not just preparing the data for the research, but actually doing the processing. And by far, most people wanted to do that at a facility of their own choosing. So if there was a data center or a processing center where the data might show up, or they could put their codes and start working on the data, they wanted the data delivered there. So it looks like people want to decimate it, prepare the data for processing close to wherever the data is stored, and then move it to where they want to do their processing. Of course, it could be done close to the repository itself. The size, and this was kind of interesting to me, that when you're retrieving data, what did people want? And the respondents, it was sort of all over the place. Most people wanted maybe 0 to 60 minutes of data, but you can see it goes all the way up to more than a month of data for 11.5% of the people. So fairly balanced there about the size. Oops, sorry. Go backwards. And then the typical size, let me see, make sure I'm in the right place. Yes. Okay. The typical size of the data that people, respondents, were looking for. They're, some were small, 1 to 500 gigabytes, but most people were looking, it looks like, at about 100 or 1 to 50 terabytes of data that they would be using for their research, and all the way up to more than 100 terabytes, and in some cases 300 terabytes. So gives you an idea of the amount of data that people are looking at and wanting to have access to. And then I found this also interesting. If we look at the distribution, we have what was sort of the longest delay that people would tolerate for retrieving a typical amount of DAS data that they use in their research. And if you can see it, oops, let's see, laser pointer. It looks like, sort of about a week. I mean, some people said it's not urgent, they could take a whole month to get the data. I would assume that that would be more or less huge data sets, but typically, 3 days to a week. So sort of on the order of days up to about a week was acceptable, and very few down at the very low end. So not a tremendous immediate demand for the data. And I think this is a reflection of the fact that they understand, that users understand that it's a tremendous amount of data and it takes a while to transfer and get it. Okay, and then sort of tying into some of the derivative products that we were talking about, the derivative products that we had, that Verónica showed on her slides were here, the 100 Hertz spatial stack, and people could select any of the ones they wanted. And so it's clear here that the 100 Hertz spatial stack to 20 meters was a very popular product, as was event segments. So in other words, looking through passive data, maybe finding, or even active data, looking for where the events are and grabbing those and putting those up. But then a fair smattering of other people for PSDs, for the very long-term information that was presented. So some of my own preliminary observations is that we have a diverse set of users that collect and use the DAS data, that keeping the data at an appropriate resolution is the most important, but keeping full resolution data would be desirable. A centralized community data repository is preferred, with pre-processing going on at the repository for decimation stacking. In other words, just getting it ready for analysis later on. Delivery of the data to some user-defined processing center for doing the research. And that people are going to be looking for data transfers from gigabytes to hundreds of terabytes. Now, of course, if you do that pre-processing at a centralized repository, you won't be transferring as much data. And that users were quite tolerant on how much time they would have to wait for getting the data. And then finally, that the most popular DAS products are the decimated stacked data sets and event segments. Oops. So let me see if I can stop this now. Guess I have to turn off my laser pointer. Can you unshare me somehow?
I will check to see if I can do that.
There we go.
All right. And are there any comments, questions, if you want to raise your hand or type them into the chat? Certainly a lot to process there. And thanks to those who are filling out the survey. Like you can also change your answers based on the discussion that's happened here if this has triggered some new ideas in you. So here's a question. A comment from Rob Casey. An acceptable wait time of days for these large data sets makes nearline affordable storage options quite viable. For example, AWS Glacier.
Well, so I think that most of the topics that came up in this survey were covered fairly well with the previous couple of talks. And I appreciate everybody who has filled out the survey and continue to do that, because we want to continue to gather community input on the metadata, on the products, on the formats and everything.
So there's a question from Jijen. Can IRIS have some similar archive service in the future, like AWS Glacier? I think that's to you, Jerry.
Yes, we are looking into it. We certainly do not have the funding to have petabytes of storage right now. So we depend on NSF to buy our hardware or to pay for the Glacier storage and so forth. So we are looking into it and seeing what it might cost to do to store these large data sets. We see across, beyond the horizon that dealing with huge data sets is something that we're going to have to address at some point. And so we're looking at it, but we don't have an immediate solution.
And here's a question from Patrick Bates. Thanks for the great talks and the initiative. I'm still surprised that so many people like Segway, SAC, mini seed files. Is there a specific reason for that?
I mini seed because it's so great, but I can't answer. I don't know. Clearly, most of the people in the survey looked at HDF5, so they're looking at more modern ways of storing the data, especially that can accommodate arrays and are self-describing. So I think that bringing the community into, particularly, I think the large data community is already adopting these formats and starting to use them. And then it's a matter, I think it was mentioned by Matt, that there's a lot of or maybe Jin, that HDF5 is a very broad format, and that we would need to settle on something that was sort of a derivative of that, or for DAS.
And yes, there's some comments about codes, existing tooling, codes that are already built to ingest, process data in those formats. A lot of, legacy. So from Boon Hoon Lai, thanks for the overview. Certain interrogators have preferred non-standard format for stability issues. For example, Solexa uses in-house TDMS format. Are we looking at storing raw data and derived products in different formats? And if we can connect them with a common metadata? So I think, yes, this is probably why we need to continue these discussions and certainly include instrument manufacturers in those conversations as
Yes.
they continue to work on these problems as well.
I mean, I don't think there's any issue with the stability at all. I think just that we have to separate what's the most convenient way to do online real-time processing of the data, and some of the ways that the optoelectronics works. And then once the data is saved, then this could be converted to different formats. So we have to separate, because again, I hear a lot of things about data, but one of the most important part of DAS technology is the application side and how the fiber is installed and what you want to do with it, because and labeling the data, because just collecting the data is not really the solution. So you have to know how you collected the data, how you label the data, what purpose you're using this for. And I think those things that Verónica showed in terms of edge processing could make a lot more sense. And we will be all happy.
Yes, and a few comments in the chat supporting that within this community, we need a standardized data format. So I'm glad we're having this conversation, and I'll just note too that we should continue this conversation. So I'm just going to post in here. If you want to join the mailing list or the DAS RCN and the working groups, especially the one working on this data management issue, then please do reach out, go to those websites and check this out. David?
Yeah, just following on from what Mahmood just said, actually. We're talking about huge quantities of data here being recorded, and quite often from an instrument point of view, these formats, the SegWi or HDF5, are not appropriate for that. You have to store the data in its binary format directly to disk, and then you have to take that data off and then do a post conversion afterwards. So just to be aware of that, because you're talking increasingly high data rates, and if you want to transfer those to disks as well, then you've got multiple RAID storages, and you have to find the most appropriate method of doing that transfer so that you don't get lossy data transfers at all, because you are talking extremely high transfer rates here. So just to be aware that there is a conversion from that binary format to these other formats.
Good point.
If I can just add a comment for that, I think right now most of the Mahmoud, correct me if I'm wrong, most of the company actually are able to save the data in the HDF5 format directly from the instrument. And I don't know, like, because HDF5 is actually quite flexible. I just don't know what's the data IO looks like if I just, because one of the issue that you save in the binary format and then you convert it to another HD5 format, for example, you need to double that storage space. And for data IO purposes, can we just read that HDF format file by file, adding in those metadata and then just save it in place? So in that way, we don't have to, create a new hard drive space and just converting the data for the converting purposes.
Yeah, I mean, even today, I mean, you can go to our user manual options, go to the saving data, and I think there is a TDMS format, there's H5 format, and AutoDemo format. So those are available already today, but also the tools that if you save in one format, you want to convert it to another format, that's possible too. And the other thing is, as a technology company, we also save some diagnostic data. So it's not just what you see. So we know there's a lot of other applications which is on the development, and things that are still the technology can be further improved. So for us, is also diagnostic data could be quite important as well. So, but I think, again, when you collect data, it's very important to know why you want to do these measurements. And if you have a goal, then demonstrating that it's possible and how it's possible is very important, because that goes into how you do the experiments, testing, collecting data, processing the data, and visualizing the data. So, and all of that, it's become part of the chain, and how you interact with that data is also very important. So, but trying to generalize everything become a bit difficult to manage. So, I mean, for example, you could do all these fast processing, and when we started the seismic applications, people wanted to go back to SegWi, and I think Doug Miller remembered that quite well. So it was almost taking some steps back. But as we know that the most inefficient way of saving the data could be SegWi, but still we have customers who are comfortable using it, and we do save in SegWi or convert in SegWi. So be flexible a bit.
So we have a couple of comments in the chat I'll read aloud. From Rob Mellors, seems like some regularized HDF5 might be a start. And from Dennis Reedy, Jijan's excellent point is that the end for which the data is collected will determine much. Perhaps that is the thinking behind the journal's request for the data, keeping the data attached to the end product and only that data.
Hello, can you hear me?
Yes, Christopher.
I have a question that goes into a different direction. But first of all, thank you for the nice talks and the discussion. We are here at GFZ in Potsdam. We are troubled by the same issues. Just one word. We've gone over to save our data on magnetic tapes, and they are stored, and it's, I think, fairly economic to save them there. And in case we want to retrieve the data and work with it, we copy larger chunks of it or smaller chunks of it onto some faster hard drives where we can access it. But my question goes out a little bit to how you handle the data and how you, on which computer you visualize your data from day to day. Do you use to copy it to your local machine and then work with your scripts and visualize the data there, or do you rather have the data on some cluster and you connect to it with a virtual machine and then do all the calculations there and just bring the plot or whatever to your screen via a virtual machine connection? I ask this because sometimes the local machines are just not fast enough and do not have enough memory to process the data, and you have to look at it at very small chunks. And I once remembered this very beautiful workshop you made where we connected to some Google server or so, and then we did all the processing there and just got the pictures and the output on our screen. So my question goes in that direction. Thanks.
So Christopher, I think you're hitting sort of at the crux of what we're trying to achieve here. You may be a little bit ahead of us at GFZ in storing lots of data that people have access to, and right now, at least in much of the community, the data are being stored individually by the people that collected the data, and there is no central repository or processing center for doing that. Maybe some of the people who are collecting and holding large data sets could speak to this more than I can right now.
So I can speak to what generally we do in our group is that we are lucky enough that we can have a big storage server where we have a copy of our data. So what I personally would do is I would take a couple of files maybe to my computer and then do some very small tests. And then when I know what I want to do, I go and I run it in the big cluster. But again, that comes back to one of the things I was touching in my talk is that I am lucky enough that I have these resources available, but not everyone would have these resources available. So I think that's something we need to consider as well, and having that opportunity to maybe do some part of the processing, or what people seem to like if from the survey, doing this decimation in somewhere close to where the data is stored, if you don't have it stored in your institution, could be a solution for that. So that's currently how I handle it at the moment. It's just like small chunks, do your test, and then run everything in a big cluster. But that's not always an option.
I can add a little bit on from my experience. So my institute, we actually invest a Windows server. You can also do a Linux server if you want to, and link that server to a data storage server. So that the student basically, Linux may be cheaper in that way. Student can just remote log in and start a Jupyter notebook remotely and just port that Jupyter notebook back to their personal laptop. So in that way, they are actually using their laptop for virtualization, but using remote, server for heavy lifting and the data transfer. But that does require a more, I would call it more upfront investment. So you're talking about, probably 60K, something like that. Type of server is a minimum requirement. A cheaper option is actually, just as you mentioned, is Dr. Ellen Martin's workshop a couple of years ago. If you can store if your university is still lucky enough to have unlimited storage for Google Drive, you can actually upload your data to Google Drive and use Google Colab, which is an online free Jupyter notebook to access the data, process that data, save it back to the notebook. The only problem is each node you have to restart it every 24 hours. So if you're willing to pay $10 per month, but that's I have all my students actually working on that route, and it is tremendous saving.
Yeah, just to follow up on that, I put a link in the chat from one of the lightning talks there that Junju Shen at Penn State did on just some tools he had put together for data visualization that just made it a lot easier. We've done any combination of sort of local scripts like Verónica was talking about to just visualize snippets one at a time. And a lot of times what I do with the larger data sets, if you want to get a more big picture view, is again using those high performance computing clusters to do sort of data products or simple metrics like how much energy is in different frequency bands, things like that, over longer periods of time, and then just moving those onto my local computer for visualization. Also, a number of high performance computing clusters are starting to do more tools for things like virtual machines and Jupyter notebooks and things like that to make it a bit easier for people to get started. So we've been looking at Virginia Tech to have that in the past year, so it's made the visualization a little bit simpler for new students to get started with as well.
Great. Thanks, everybody, for sharing your experiences. We have 2 minutes left, and I think Casey is ready to close us off here. So,
well, thank you so much to all of the webinar organizers, our presenters, and to everyone who's been participating in this important discussion. The recording will be made available on the IRIS Earthquake Science webinar playlist. If you're interested in future DAS webinars, please join the DAS mailing list and check out the DAS RCN website. I'll go ahead and share those links that were shared in the chat, so you'll find those below the description of the recording, so you won't miss those either. But thanks so much for everyone who showed up today.
Thanks, everyone.
Thank you, Casey. Thank you. Thank you for organizing.
Thank you, guys. Thank you.
thanks, everyone.